Welcome to Gnana Taranga, NET CET coaching classes. This program is organized by Department of Pre-University Education, Government of Karnataka. Myself, Vijayendra ji, I will be covering topics on semiconductor electronics and communication systems. Let us go through some synopsis points. Semiconductors are integral part of modern electronic circuitry. Semiconductors have high resistivity compared to metals, and they have negative temperature coefficient of resistance. What is the meaning of negative temperature coefficient of resistance? When you say alpha is negative, it means that as temperature increases, resistivity and hence resistance decreases. And temperature, when it decreases, resistivity and hence resistance of the material increases. Classification of semiconductors. Now, semiconductors are broadly classified into elemental type and compound semiconductors. In elemental type, you have pure materials, silicon and germanium, and in compound semiconductors, inorganic as well as organic materials will be there. In inorganic, examples will be gallium arsenide, gallium arsenide phosphide, cadmium sulfide, etc. Organic will comprise of materials like anthracene, polypyrrole, etc. Now, based on energy bands, we can distinguish between metals, insulators and semiconductors. Essentially, energy band comprises of closely lying energy levels corresponding to electrons in different state. Now, electrons, if they are free electrons, conduction electrons, the energy levels lying close by corresponding to those electrons are called or they are going to constitute conduction band. And valence band comprises of energy levels which lie very close by corresponding to valence electrons. And there may be a small gap, marginal gap or large gap depending on the material between conduction band and valence band. Now, this we call as energy gap. As we can see in this picture, in the first case, when we take metal, very small energy gap can persist in some cases, or there may be overlapping of these two bands. Now, this scenario is there for metals, which are good conductors of electricity, and as such, since there is an overlapping here, many electrons are available for conduction and hence metals are good conductors. Free electrons are available in this band. Coming to insulators, now these lack free electrons, that is, free electrons are not in abundance here. The valence band and conduction band are separated by a large energy gap. Generally, we say that if energy gap is more than 3 electron volt, then that can be categorized as an insulator. And usually, the conduction band will be empty, valence band will be filled. Coming to semiconductors, the energy gap between valence band and conduction band is very small. In case of let us say germanium and silicon, the energy gap will be of the order of 1 electron volt, 0.72 electron volt maybe for germanium, 1.12 electron volt for silicon. And we can say that if energy gap is less than 3 electron volt, then it will be a semiconductor. Then classifications based on what kind of semiconductor we have. In semiconductors, we have intrinsic semiconductor and extrinsic semiconductor. Intrinsic generally means pure semiconductor, where we won't have doped that with any impurity atoms. If we dope, that is, doping basically is method of adding impurity atoms to the crystal structure of germanium or silicon so that the conductivity of those materials enhance. And in extrinsic semiconductor, you will have N-type and P-type semiconductor, basically what we call negative type and positive type. When you take pure crystal of silicon or germanium, they are both of them are tetravalent, and we can see in this particular picture the two-dimensional array of atoms. Here another charge carrier comes into picture. Usually we have electron as the charge carrier. Even hole, what we generally see in this particular picture here, that also is a charge carrier, which is the positive counterpart of electron. And how are these holes created? Let us say at very low temperatures, maybe close to 0 Kelvin, we can say that almost all the electrons are taking part in the bonding process. None of them are free, and therefore you don't get any of these covalent bonds sort of appearing broken. But as we increase the temperature, the amount of thermal energy is sufficient to break some covalent bonds, and some of the electrons may move out. So here is one thermally generated free electron. It has become free. At the same time, it has left behind one vacancy in this particular site. Now this vacancy left behind by an electron, when it goes out of that bond, is what we call as hole. It will be associated with a positive charge that is given by this particular ion, the atom which has lost that electron locally. So if one electron is made free, one hole also will appear. It means that you will always get electron and hole pair created. So this EH pair is created due to thermal energy. And how is this hole going to help us in conduction? We can see in this particular picture that this electron from one particular site in the covalent bond is migrating to another. So if the electron goes that way, the hole comes the other way, because that electron is going to leave behind vacancy. Now this way we can say, when a field is applied, in the direction of the field, electric field, positive charge entity, the hole can move. In the direction opposite to that, electron will move. Energy band diagram, if you consider for intrinsic semiconductor, you can see that at 0 Kelvin, all the electrons are in the valence band. None of them are in the conduction band. It means that this material, even though it is a semiconductor, will behave like a perfect insulator close to 0 Kelvin. Coming to another picture, to the right you can see here, temperature is more than 0 Kelvin. That is probably, let us say, at room temperature we can consider. Electrons in the valence band will get sufficient energy so that they will move over to the conduction band, and conduction band there is some occupancy here. Since they are free electrons, they take part in the conduction process. It means that as temperature increases, conductivity enhances. Coming to extrinsic semiconductors. When you say extrinsic semiconductor, these are obtained by doping pure semiconductors like germanium and silicon. Based on what we dope them with, you get N-type and P-type. Usually, when we add pentavalent impurities like phosphorus, antimony, bismuth, etc. to the pure crystal of semiconductor germanium and silicon, you will be getting N-type semiconductor, negative type what we call. And in this particular picture you can see that one such impurity atom is added to the crystal structure of a germanium or silicon for that matter. See, this being pentavalent, an additional electron is there along with the 4 electrons which take part in the bonding process. That way we can say that a pentavalent impurity added to the crystal structure contributes or donates one free electron to the crystal structure. So if we have added some 100 such phosphorus atoms, 100 free electrons are available. Generally, when doping is done, it will be done with one particular ratio. Host atom to impurity atom ratio usually will be 10⁻⁶:1. That is, for every million host atoms, you will be having one impurity atom added. To the right of the screen, you can see energy band diagram is given. In that, you can see that there is this level, donor level, that has arrived in the forbidden band. Usually in the forbidden gap, no energy level will be drawn, but this is because of the addition of impurity atoms that we have here. You are going to have the donor level. That will be extremely close to the conduction band. So little bit of energy is sufficient for the electrons to jump across to increase the conductivity. More number of free electrons are available. So students, remember, in N-type semiconductor, free electrons are majority charge carriers. So we can say that Ne is greater than Nh. Whereas in case of intrinsic semiconductor, number of free electrons will be equal to number of holes. But in this particular case, number of electrons will be more. Therefore, electrons or free electrons are called majority charge carriers. Coming to the next one, P-type semiconductor. Now this material is obtained by doping pure semiconductor with trivalent impurity atom. Example, aluminum, boron, etc. When you add them, you are going to get holes more, because you are going to have only 3 electrons here from the trivalent impurity. So it always can take in other electrons. If another electron from the host atom jumps into this, as you can see in this picture, the electron actually creates a hole there. If it comes here, the hole is created, or if an electron goes that way, hole is created there. So number of holes will be more in case of P-type semiconductor. So in this particular case, we can say NH is greater than Ne, which means that holes are majority charge carriers and electrons are minority charge carriers. You can see that there is a acceptor level here. So little bit of energy can get some of these electrons jump to that, and then that creates additional holes, as you can see here. So that way, number of holes will increase in case of P-type semiconductor. Now when you are having this P and N materials, what is the application part of it? Now we have what we call PN-junction. It is also referred to as diode. Now in this particular picture, you can see in a single crystal, you are going to have the P and N materials, and sort of in a single crystal they are developed, so that near the boundary what happens, this is what we call as depletion region. Now how does that come into picture? When you say that P-type material is there, holes are majority charge carriers here. N-type semiconductor, electrons are majority charge carriers. So when holes are majority here, due to diffusion process, holes will migrate from there to here, and from N-type side, electrons will come to the P-type side. So due to this migration, what happens, or diffusion rather, I should say, you will be having immobile ions developed near the junction, near the border. Now these immobile ions are responsible for depletion region. So for depletion region to be developed, majority charge carrier diffusion is the process, and usually this depletion region width will be a micrometer thick, and biasing etc. will be done. Biasing generally means you are connecting a source of EMF across the PN junction. When you do so, depending on how you make connection, either the depletion region width decreases or it will increase. Now this is basically forward bias. When you say forward bias, you are going to have positive terminal of the cell connected to p-type material, negative terminal of the cell connected to n-type material. Now when P to P, N to N connection is established, and when you increase the voltage gradually, you will find that the depletion region width decreases, even junction potential barrier height also decreases. And in the process, as you can see in this picture, without bias, the height of the potential barrier is so much, and with forward bias, there is a decrease in that height. And a forward biased PN junction offers small amount of resistance. Reverse bias, when you consider, as you can see in the picture, the positive terminal of the cell is connected to N-type, negative terminal is connected to P-type. Now this means that the depletion region width is going to increase in width. As you can see in this picture, immobile ions are piling up more, and without bias, whatever junction potential barrier height is there, that will increase further, making diffusion almost impossible. Like a drift is going to happen in reverse bias because this particular plus and minus ions will develop a field in this direction. So from positive to negative, that is positive in the sense that you are going to have plus ions piled up here, minus ions piled up here, plus to minus, the direction of the electric field will be there. So in that sense, N-type side will be at a higher potential, P-type side will be at a lower potential. This field can cause the drift of charge carriers, minority charge carriers, and drift is the major process that happens in reverse bias. Diffusion is the process that can be the mechanism for conduction in the forward bias. And a PN junction diode will have some resistance. The characteristics you can see here. For a particular change in the voltage, corresponding change in the current, delta I is there. So delta V to delta I will give dynamic resistance of the device. Usually this resistance will be small for diodes, forward biased case. In reverse bias, the resistance will be large. It can be several kilo ohm or mega ohm also. And diode application, if we come to, rectification is a process. Basically rectification means converting an AC into DC. You may not get perfect DC, at least you will get pulsating DC. So as the diagram you can see here, there is this AC input, and using a transformer, step down transformer, you are going to decrease the voltage, and that is fed to the diode, and the diode will act like a rectifier. So now during, let us say, this positive half cycle of the input AC, A will be at a positive potential and B will be at a negative potential. During that period, the diode conducts. Therefore, you will realize an output voltage here. Whereas during the negative half cycle of the input AC, this end B will become positive, A will become negative. So you can see that anode of the diode is given to negative part. Therefore, the diode will be reverse biased and it will not conduct. If it doesn't conduct, no current will flow through load resistance RL, and hence you will not realize any output voltage. So halfway rectifier, as the name itself suggests, it will conduct only during one half cycle of the input AC. In the full wave rectifier part, two diodes are employed, D1 and D2, and one after the other respectively during positive half cycle and negative half cycle, one or the other will be conducting. So you will be getting output for the entire input cycle. During the input AC positive part, you can see A will be at a positive potential with respect to center tap C, and B will be at a negative potential. So diode D2 is reverse biased, it does not conduct. D1 is forward biased, it will conduct. So when D1 conducts, you realize an output voltage here as shown in the diagram, waveform picture. And in the negative half cycle of the input AC, B will be at a positive potential, A will be at a negative potential. It means that D1 does not conduct, D2 conducts. When D2 conducts, again you are going to get output voltage realized, and you will be getting successively voltage output for both the half cycles of the input AC. Coming to another type of diode, this is called Zener diode. Usually Zener diode will be operated in the reverse characteristic. In the diagram you can see that there is a breakdown voltage here, Zener breakdown we generally refer that to, and in that particular region, even as the current is shooting up, voltage is maintained constant. Now this nature of Zener diode makes it useful to be operated in circuits like voltage regulators. We have special junction devices, optoelectronic devices, and in these optoelectronic devices we either source or detect or control photons, that is light. Some of the optoelectron devices are photodiodes, LEDs, and solar cell. In photodiode, as the picture suggests, light is required, so ambient light can fall on the device. Usually this diode is operated in the reverse bias mode, because as it is in the reverse bias mode, not much of current will be there, and when light falls on the junction here, it is photo excitation that is happening. So you are going to have energy absorbed by the device, and electron hole pairs are created near the junction. Holes are pushed towards the P type and electrons towards the N type, and this actually enhances what you say reverse current. In the absence of light, very small reverse current can be there, and with the application of light, you are going to have an increase in the current. Now this actually is the essence of detection of the incident light. And light emitting diode is another kind of diode. Here light is emitted by the device, spontaneous radiation, once it is suitably forward biased. As you can see in this particular diagram, electron hole recombination takes place under forward bias, and recombination, when it takes place, the energy will be released in the form of photons. Solar cell is another junction device, and it will generate EMF when solar radiation falls on the device. And radiation falls on the device here, electrons and holes so generated will be pushed respectively towards the N type and P type. They will be collected by the respective electrodes, and the minuses piled up on one side and plus on the other side will develop the EMF. The IV characteristics of photo cell is shown. Now this is what we call open circuit voltage, that is when you are not using the device, complete voltage or EMF is available, current will be 0, and this is short circuit current. When you draw completely the entire current, voltage will be 0, but current will shoot up. Now transistor is another device based on semiconductor technology, and it has 3 regions, semiconductor regions, emitter, base, collector, and the doping concentration of these 3 will be different. Usually emitter is heavily doped, collector is moderately doped, and base is very lightly doped. And you can see in the picture the relative sizes or widths of these regions also. Base is very narrow, thin, collector is broad, moderate size will be there for emitter. and usually transistor is used for amplification purpose. And one more thing is, in case of the distinction, NP and PNP transistors are the two junction transistors that are available. They are also called bipolar junction transistor, BJTs, and the circuit symbols you have to be careful about. Here the arrow is shown outwards, here the arrow is shown inwards in the PNP transistor. In this case, you can remember NPN transistor like arrow not pointing in, the arrow is pointing out. Basically, the arrow represents the conventional flow direction when you are using the transistor in a proper manner. And when you bias, usually emitter based junction is forward biased and collector based junction is reverse biased. Application for transistor, you can use it as a switch and an amplifier. This is the transfer characteristics of the transistor. You will see that input voltage is there and corresponding output voltage, and there are three regions here: cutoff region where the transistor generally does not conduct, active region, and the saturation region. When you are using transistor as a switch, you are going to have cutoff region and saturation region operating, that is, those two will be useful. And in the active region, when you are going for, it is generally used for amplification purpose. Transistor is also used as an oscillator. Now, principle of transistor oscillator is that it can be a self-sustained transistor amplifier where you go for positive feedback, in phase feedback. We come to logic circuits now. This logic circuit basically it works on the principle of Boolean algebra. You will have some three basic gates: OR gate, AND gate, and NOT gate. The first one is OR gate. It is such a gate that its output will be high. Generally, when you say high, you write 1. If it is low, it will write 0. It is not that 1 means 1 volt, 0 means 0 volt. So, this gate is such that its output will be high even if one of the input is high, as you can see here. If both inputs are high also, it will give high. Coming to the next gate, AND gate. This is a logic gate where only if both inputs are high, it will give a logic high. Otherwise, even if one of the input is low, it will give low output. And the next one is NOT gate. Now, this is also called logical inverter. This is a single input, single output gate, and whatever input you give, the logical inversion you will get as output. For example, if you give 0 as the input, low voltage, you get 1, it means high voltage. You give 1, it will return with 0. The next one is a NOR gate. A NOR gate functions like a combination of OR gate coupled with a NOT gate. That is, OR gate followed by a NOT gate. Whatever output we have seen in case of OR gate, the output of OR gate is seen to be inverted here. So, you will have A plus B or A or B with a complement. We call it as A plus B whole bar. So, if you remember the case of OR gate, you got 0, 0, 0, but it is inverted here. 0 inversion is 1. In all other three cases, you are going to get 0 because earlier it was returning with 1. And the last gate is NAND gate. NAND gate is a AND gate followed by a NOT gate. So, its output will be logical inversion of A and D, AND gate output. So, you have AB as ANDing, inversion represents AB bar. So, it only means NAND gate will give an output which is exactly the logical inversion of AND gate. Both these NOR gate and NAND gate, they are called universal logic gates. Now we will go through communication systems. Communication essentially is the process of or act of transmission of information. When you want to convey information, there are two basic modes. Either from point to point you can convey that, like telephones, person to person, point to point, or it can be broadcast type like radio and TV. One transmitter will be there, multiple receivers are going to be there. And in any communication system, you should have a basic infrastructure. And what are the essential parts of this communication system? The block diagram is very indicative of that. You should have an information source, what message you have to convey, but directly you cannot convey it like that. You have to process it. So using a device, you are going to, like a transducer, convert that into message signal. And then there must be a transmitter, as you can see here. It transmits the signal. Through what it will transmit? You require a medium. That medium is called channel. And the channel, from the channel, you will get it to a receiver. A receiver is a device basically which retrieves the information, and that will be made to reach the user after some processing is done, so that the decoded version, the information will be reaching the user of the information. In the process, what happens? Some unwanted signal also combines. That is what we call as noise. And students, please remember certain basic terminologies you should be aware of. Only few I have highlighted here. Transducer, for example, attenuation, amplification, modulation, demodulation, repeater. Essentially, transducer is a device which converts energy from one form to another. Now, if you are, for example, converting sound into electrical signal, now that itself is a transducer, like microphone, etc. Attenuation happens when communication takes place. Basically, attenuation means reduction or loss of signal strength when signal is being communicated. Amplification is a process wherein energy of the signal is increased. So if you are increasing the energy of the signal, that is what we call amplification. Modulation, demodulation are two essential components of communication. Modulation is a process wherein some feature of high frequency carrier wave is altered in accordance with instantaneous value of message signal. And once you do that, it is something like you are coding your information. It will not be directly sort of available to the user. You have to demodulate it, decode it. So demodulation is a process wherein you detect that particular signal, retrieve what is the essential component, the message signal, and leave the high frequency carrier wave. Repeater we require because if signal strength during transmission decreases, you require repeaters that may consist of or comprise of again some amplifier, receiver and transmitter. So if receiver is there, it will receive that weak signal, amplify it, further strengthen it, and then it is going to retransmit it. Likewise, you have bandwidth and range of the thing, and then noise, signal, other definitions and terminologies are there. Students are advised to go through all those. And some of the communication frequency bands are given. Just you have to commit certain numbers to your memory, like standard AM broadcast, less than 2 megahertz it will be there. FM stations generally operate between 88 to 108 megahertz. You will have so many FM stations playing, you know the frequency ranges. Television will operate up to some 800, 900 megahertz, ultra high frequency ranges. Cellular mobile will operate from 840 up to 935 megahertz. Satellite communication will be there in gigahertz, and uplink downlink frequency ranges are generally different. Modes of propagation. If you want to send waves, in what ways you are going to send them? One is ground wave or surface wave propagation. Usually we go for low frequency signals, maybe up to some 2 megahertz like that for ground wave propagation. Otherwise, higher the frequency, greater will be the attenuation. Sky wave propagation in fact is facilitated by the ionospheric layer, and the electrons will respond to certain frequencies in those layers of the Earth's atmosphere, and via reflection you are going to get the sky wave back to the Earth to different points of reception. So usually we go by 3 megahertz to 30 megahertz therein for sky wave propagation. Beyond that, if you send the waves, the carriers more than 40 megahertz up to some gigahertz, etc., space wave propagation is the mode for propagating the radio waves. As you can see in this particular picture, sky wave propagation, how exactly different layers, atmospheric, ionospheric layers are helping the reflection. Once a particular frequency is shorted towards the layers, depending on the angle and the response of the electrons, the waves are going to be reflected back, and reception will happen, and that will enhance the range of the transmission. And different layers of atmosphere, and in what part of the day and night they are active, how do they help propagating electromagnetic waves, which part of the electromagnetic wave spectrum they help. This table will tell you troposphere, the D layer, E layer, F1, F2. Kindly go through those things. Then when you say line of communication, line of sight communication, LOS, via space waves, you have a transmitter here and receiving antenna here, and this is what you call the transmission range. And from here to here, if direct line of sight communication happens, for that what is the distance that is suggested? There is a formula which gives you that D equals root of 2RH, where R is the radius of Earth and H is the height of the antenna. Now dt represents the radio horizon for transmitter, and this other part represents the radio horizon for receiver. So total, if you want to get the distance, you have to double this particular value. This is overall picture of different modes of propagation of electromagnetic waves. You have this ground wave propagation here, direct line of sight also, and ionospheric layers are reflecting, and the communication satellite is there. In fact, communication satellite will be a repeater station in space. So directly it will receive from the transmitter and retransmits that to different locations that are designated. And the process of modulation is very vital for communication. Without modulation, we cannot send waves. Ordinarily, when you are having a message signal, it is a low frequency signal. If you are sending that, a lot of energy loss will be there, and therefore you need to modulate. If you just go by sending those waves without modulation, impractical antenna lengths will be there, which extend up to several kilometers. Therefore, modulation is very much essential. In modulation, there are three types: amplitude modulation, frequency modulation, and phase modulation. And in this particular graphical picture, you can see the waves that are given here. This is high frequency carrier wave, and this is the modulating signal, the message signal. In modulation, you are going to superimpose the low frequency message signal onto the high frequency carrier, so that one of the characteristic feature of the carrier wave is altered, and that will enable the propagation of radio waves. So in the first picture here, you can see amplitude modulation is the process. The high frequency signal, the frequency is remaining the same, only thing is its amplitude is changing. As you can see, the amplitude is changing here, and in the second one, it is frequency modulation. In accordance with the instantaneous value of the message signal, the frequency of the carrier is modulated or changed. Similarly, you have the phase modulation here. And when amplitude modulation takes place, the original carrier frequency is there. Along with that, two more components will come. These are side bands, what we call. This is lower side band, which is the difference between the frequencies of the carrier and the modulating wave, and the other one is upper side band, where you are having omega c plus omega m in terms of angular frequency, or directly you can say fc plus fm, fc minus fm also. Now, in the side bands also information will be stored. And in this diagram, block diagram, you can see how basically a transmitter functions. You are having the message signal fed to a amplitude modulator. It actually modulates the carrier in accordance with the message signal, instantaneous value, and once that is done, before transmitting, you have to increase the power level of it. So, power amplifier is there, and then it will be transmitted via an antenna. Demodulation is a process where you recover the modulating signal from modulated carrier wave. Like already there is a coded version, you want to decode it. Now, in this particular picture, this is a block diagram of receiver. Once you receive the carrier, high frequency modulated carrier, now this will be taken and it will be a sort of a weak signal. It will be amplified. In the intermediate stage, the beat frequency is taken, it will be fed to the detector, and then the detector will retrieve the message signal, and again it will amplify it, and the output of that will be used by the user of information. And this block diagram is basically how an AM detector works. The amplitude modulated wave is shown in this. It will be passed through a rectifier, which will filter out the negative components, only the positive is taken. Again, this is actually a mix of high frequency part and the modulating signal, message signal. And envelope detector, what it does, it separates the high frequency component from audio signal or message signal, and you get the message signal at the receiver output. Now, this is how essentially the communication system works. Now, we will take up some questions. Now, this question is related to the first part of the discussion, that is the electronics part. Carbon, silicon and germanium have 4 valence electrons each. At room temperature, which one of the following statements is most appropriate? The number of free conduction electrons is significant in carbon, but small in silicon and germanium. The number of free conduction electrons is negligibly small in all the 3. The number of free electrons for conduction is significant in all the 3. The number of free electrons for conduction is significant only in silicon and germanium, but small in carbon. Basically, carbon, silicon and germanium, all the 3 are tetravalent. But then carbon has lot of energy gap. The energy gap in carbon is more compared to silicon and germanium. So, it cannot be categorized as a semiconductor. So, at a given temperature, you will find more number of free electrons in only silicon and germanium, because the electrons can jump from valence band to conduction band easily, but not so in carbon. Hence, the answer to the question will be D. The number of free electrons is more significant only in germanium and silicon, but it will be small in carbon. The second one, a piece of copper and other of germanium are cooled from room temperature to 80 Kelvin, then which of the following would be a correct statement? Resistance of each increases, resistance of each decreases, resistance of copper increases while that of germanium decreases. Resistance of copper decreases while that of germanium increases. Remember, copper essentially is alpha positive and germanium is alpha negative. It is semiconductor material. What is the meaning of that? You are now cooling. So when temperature decreases, in case of copper, since it is alpha positive material, there should be an increase in resistivity and hence resistance. Rho and R both will decrease because temperature is decreasing. In case of germanium, since it is alpha negative, when you are cooling it, the resistivity as well as resistance should increase. So the answer will be D. Resistance of copper decreases while that of germanium increases. In a N-type semiconductor, which of the following statements is true? Holes are majority charge carriers and trivalent atoms are dopants. Electrons are majority carriers and trivalent atoms are dopants. Electrons are minority carriers and pentavalent atoms are dopants. Holes are minority carriers and pentavalent atoms are dopants. Remember, this is N-type semiconductor. In N-type semiconductor, electrons are majority charge carriers, holes are minority charge carriers. So either you have to go for where holes are minority is given, or electrons majority are given. And that too, since this is N-type semiconductor, pentavalent impurity should be there. So search for the combination where pentavalent atoms or dopants are given, along with either they should give holes minority or electrons majority. Now as you can see in this picture, or rather in this slide, holes or minority is given in the last option along with pentavalent atoms or dopants. So this is the answer. Next question, which of the following statements is true? Doping of pure germanium with trivalent impurity gives N-type semiconductor. Resistivity of pure germanium increases with temperature. Majority carriers in P-type semiconductors are holes. Doping of pure germanium with a pentavalent impurity increases resistivity. Now they are asking which one is true. Now C, if you take C, majority carriers in P-type semiconductor are holes. In P-type, holes are majority charge carriers. So C is the answer in this particular case. And you can check why others are not okay. You go for the first one, doping of pure germanium with trivalent gives N-type. When you say trivalent impurity, it should give P-type. And why the second one is wrong? Resistivity of pure germanium increases with temperature they have given. When temperature increases, germanium being negative alpha material, when temperature increases, resistivity should decrease, but they have given increases. And when you dope germanium or silicon with any kind of impurity like pentavalent, trivalent, it should increase conductivity, not resistivity. Hence C or D also is not correct option. C is the option. Fifth one, pure silicon at 500 Kelvin has equal number of electron and hole concentrations. They have given the number. Doping by indium increases NH to 4.5 into 10 to the power of 22 per meter cube. The doped semiconductor is. Now when you are having this situation, you will go by this relation Ne into NH is equal to Ni square, where Ni is called intrinsic carrier concentration. They have given in this particular case Ni, that is this value, and since it is doping by indium, this is NH value. So they are interested in knowing what is Ne. So Ne will be equal to Ni square by NH. I will take it like 1.5 square, 10 raised to 6 and 16 is 32, entire thing divided by 4.5 into 10 to the power of 22. Now this will cancel it 3 times, this will cancel this twice. You are going to have 1 by 2, that is 0.5 into 10 raised to 32 minus 22 is 10. Either you can say 0.5 into 10 raised to 10, or you can write it like 5 into 10 to the power of 9 per meter cube. Now you have to choose which is your choice, and only one option has 5 into 10 raised to 9, so you need not even bother to check anything else. But you should be careful, since it is indium that is being sort of used as dopant, you are going to get p-type material, so B is the answer. Sixth question, the dominant mechanism for motion of charge carriers in forward and reverse bias silicon PN junctions are. See, when you forward bias a diode or a PN junction, diffusion is the one that is a major or dominant mechanism, and when you reverse bias, what happens? The depletion region width increases, the electric field becomes strong. Under the action of electric field, there will be drift of the charge carriers, especially that of minority carriers. So we can choose the answer where it says diffusion in forward bias and drift in reverse bias. So the answer will be B, diffusion in forward bias and drift in reverse bias. Coming to the next question, in a PN junction diode not connected to any circuit, that is unbiased case, option A, the potential is the same everywhere. Second one, the P type is at a higher potential than the N type. C, there is an electric field at the junction directed from N type side to P type side. D, there is an electric field at the PN junction or the junction directed from P type side to N type side. See, when you are having this PN junction, the junction depletion region, if this is P type and this is N type, you are going to have pluses piled up here, minuses piled up here. On the P side, it is minuses, that is the immobile negative ions. On the N side, immobile positive ions. Always the field is from plus to minus, that is plus which lies in the N type side to minus which lies in the P type side. So electric field direction will be from N type side to P type side, and potential is same everywhere they have given. Potential will not be same everywhere, because since this N type side is having positive immobile ions, it will be at a higher potential. So if you were to write the potential graph, it will be like this. So this shows that N type side is at a higher potential, P type side at a lower potential. Hence the answer will be choice C. There is an electric field at the junction directed from N type side to P type side. In an unbiased PN junction, holes diffuse from P region to N region because free electrons in the N region attract them. They move across the junction by the potential difference. Hole concentration in the P region is more as compared to N region. All of the above. Now generally when you say holes diffuse from P region to N region, essentially diffusion is a process which depends on the concentration gradient. If holes are diffusing, naturally it means that in the P region they are more in number, hence they are diffusing to the N region. So the answer will be C. Hole concentration in the P region is more as compared to N region. Ninth one, pick out the statement which is not correct. Whenever you get a question that untrue, not correct, etc., please mark it so that you don't go wrong there. So they are asking which one is not okay. First choice, at a low temperature, the resistance of a conductor is very high. So semiconductor at low temperature, it has high resistance, they are telling, and that is true, so you cannot go for that. Movement of holes is restricted to the valence band. This is also okay. Either you can represent holes and the movement of holes either in the valence band or in the covalent bond. So that is okay. C, width of the depletion region increases as the forward bias voltage increases in case of NP junction diode. It means that you are increasing forward bias and they are saying width of depletion region increases. With forward bias, essentially what happens is depletion region width decreases, even junction potential barrier height also decreases. But they have given just the opposite. So the wrong one that they want is C. You can just check the last one. In a forward bias condition, the diode heavily conducts. This is true because in the forward bias condition, the depletion region width decreases, enabling majority charge carriers to move across the junction, enhancing the conductivity. So the answer for this question is the third choice, C. A potential barrier of 0.5 volt exists across a PN junction. If the depletion region is 5 into 10 raised to minus 7 meter wide, the intensity of the electric field in this region is, they have given. Now, if you want electric field, see you have electric field value is like dV by dx. Negative potential gradient, okay, but we just want the magnitude, so I have added the minus sign there. Here they have given potential barrier height to be 0.5 and the depletion region width is 5 into 10 raised to minus 7. You can write it like 5 into 10 raised to minus 1. This is 5 into 10 raised to minus 7. So this will go. This leads you to 1 into this minus 7 when it goes to numerator it becomes plus 7. So that leads you to 10 raised to 6. So the answer will be 1 into 10 raised to 6 volt per meter, which is choice A. Of the diodes shown in the following diagrams, which one is reverse biased? Now when you want to check forward bias, reverse bias, one thing that you have to bear in mind, like maybe you would have been taught like P to P, N to N is forward biased, and if it is P to N and N to P is reverse biased. When you say P to P, positive terminal of the cell is connected to P type, negative to N type. So this is forward bias, but they have not asked forward bias, so this is ruled out. Now the other one is, if P type is given to negative terminal, N type is given to positive terminal, then it is reverse biased. But then the diagrams will tell you that there are different ways in which you can, they have biased it. Negative potentials are made use of, grounding is made use of, positive potential is made use of. Let us take one by one. In diagram A, you find cathode, this is N type, cathode is connected to more negative and anode is connected to less negative. It means more positive. So this is forward biased. So this is forward biased. Coming to second diagram, you find this is grounded. The P type is grounded 0 volt, we can say, and cathode is more negative. This also represents forward bias. And coming to C, you are having this anode grounded 0 potential, cathode is at a higher potential 5 volt. Now this is where you find reverse bias, it looks like, because cathode is N type, it is given to higher positive, whereas P type is grounded. And just to rule out the other one, we will just go through the last one also. You will find anode at a much higher potential, cathode at lesser positive potential. So this also is forward biased. So the answer here is C, that is reverse biased case is this diode. 12th one, the circuit shown in the following figure contains two diodes D1 and D2, each with a forward resistance of 50 ohm and with infinite backward resistance. If the battery voltage is 6 volt, the current through 100 ohm resistance is. See, we have to check in this particular diagram which diode is forward biased, which is reverse biased. The positive terminal of the cell in this case is connected to cathode. So, this negative has gone to anode. So, this diode is reverse biased. It does not conduct because they say it is infinite resistance. It means this entire line we can ignore. Current cannot flow through this. Then what happens? The current will flow through this because this is forward biased. This is P type and this is N type. Positive is connected to positive. So, only the outer part will come for calculation. And they say forward resistance of diode is 50 ohm. So, there will be 50 ohm here. Now, you just count. 50 ohm plus 150 ohm is 200 ohm plus another 100, 300. So, total resistance is 50 plus 150 plus 100. That leads us to 300 ohm. Now, if you want to calculate current I, it is voltage by resistance. Voltage they have given 6 volt. 6 divided by 300. So, 6 will cancel it 50 times. 1 by 50 means 0.02 ampere. So, the answer is B. See, students, in this particular circuit, they want to know which will not show current in the ammeter. Now, current will not flow in the ammeter only if that line does not carry current. And when that happens when the diode is reverse biased and it does not conduct. So, in the first picture, let us go to, this is a diode where it is N type and this is P type and it is connected to positive here. Therefore, this is reverse biased case. A reverse biased PN junction does not conduct. So, and even though the other one is there, since this is already reverse biased, it will not conduct. Probably this is the answer now, but we have to rule out the other ones. In this B, both are like forward biased, so they will conduct. Here it is actually a dual path. This is forward biased because this is plus, it will conduct. So, the current can always pass like this. Even if this does not conduct, it is okay. The ammeter can have current in it. Here both of them are conducting, therefore, this also will show current. So, the first one is the answer, where you are having this reverse biased. So, answer for this question is A. A PN photodiode is fabricated from a semiconductor with a band gap of 2.5 electron volt. It can detect a signal of wavelength. Now, in such situation, what you can do? Go by calculating the energy gap. Energy gap is given by E equal to Hc by lambda. Now, you want to calculate what is that lambda. So, you can say Hc by Eg. Now, lambda will be, please remember, Hc can be given by 12,400 electron volt angstrom, that you divided by Eg, energy gap they have given 2.5 eV, EV cancels, and what you can do is, just to make your calculation easier and faster, you can multiply both by 4, so that 2.5 into 4 is 10, that will cancel one of the zeros there. This translates into 1240 into 4 angstrom. So, that works out to be like 4,960 angstrom. Now, it means that any wavelength which is greater than this will not be able to cause excitation, so it will not be detected. So, for you to have the photodiode working, any wavelength that falls on this device should be having lesser wavelength than this. The first one you can rule out because it is 6000 angstrom. Second one is 4000 nanometer, but then it is 4000 nanometer. So if you convert that into angstrom, it will be 40,000. This also you can rule out. This is 60,000. So choice will be 4,000 angstrom, D. In the given figure, a diode D is connected to external resistance R equal to 100 ohm and an EMF of 3.5 volt. If the barrier potential developed across the diode is 0.5 volt, the current in the circuit will be. Since they say 0.5 volt will drop across the diode only to overcome that barrier, then the rest voltage out of 3.5 will fall across the resistor, which is 100 ohm value. So current will be simply 3 by 100, which means it is 0.03, or in terms of milli, 30 milliampere. So answer is D. A Zener diode having breakdown voltage equal to 15 volt is used in a voltage regulator shown in the figure. The current through the diode is. Now what we can do is, since Zener and this resistor are in parallel, you will get 15 volt here easily. Out of 20, if 15 is falling across Zener, then rest 5 volt will fall across this series resistor. I can say that there is a current IS here, and it splits into I load resistance and I Zener. So you can calculate IS first, voltage by resistance, 5 divided by 250. So this is 1 by 50. 1 by 5 is 0.2. 1 by 50 is 0.02. Or it can be taken as 20 milliampere. This is the series resistance current. And you can come to the last part, that is 1 kilo ohm resistor. Here IL, you can calculate it like 15 volt divided by 1 kilo ohm, which amounts to saying it is 15 milliampere. And now what you do, apply junction rule. You have IS equals IZ plus IL, and you want to know what is IZ, it will be IS minus IL. Out of 20 milli, if you subtract 15 milli, then it will be 5 milliampere you get, which is choice B. The given graph represents VI characteristics for a semiconductor device. Students, we have already seen this kind of graph in the synopsis. Now in this, the fourth quadrant is made use of. Generally, when you supply voltage to a device, either you will make use of the first quadrant or the second one, and hence this device will act like a source of EMF, which will be solar cell. So you can zero in on either C or D. So in which case, go through that. It is a VI characteristic for solar cell where point A represents open circuit voltage. This is open circuit voltage, and B short circuit current. So this is the correct choice. Now next diagram, there is of course this full wave rectifier given. Input AC is given. So rectifier, what it will do, it will give you an output like this, which is a pulsating DC. But if you want a smooth DC, you have to go for filter. This part what they have given, this is the filter part. This is a shunt capacitor filter. The output of this will be given in D. Other three are not okay. This is the one, generally because in that filter you will be getting initially the output voltage increasing like that. Due to capacitor action, you will be getting the output like this. So along with resistor and capacitor, the filtering action is done that way. So the output, proper output will be as given in choice D. If L1, L2, L3 are the lengths of the emitter, base and collector of the transistor, then you know that when it comes to the size or dimension, collector is the one which has maximum one. So, we can say L3 is the greatest, and emitter will have moderate size. So, L3 greater than L1, and base always will be having lesser thickness. So, that comes second. So, it is essentially L2. So, L3 greater than L1 greater than L2, the choice will be D. When NPN transistor is used as an amplifier, electrons move from base to collector, holes move from emitter to base, electrons move from collector to base, holes move from base to emitter. In an NPN transistor, majority charge carriers that are going to be given from the emitter is electrons. They move from emitter to base first, and then they will be collected by the collector. So, you can say in which of the cases that is true. They have given electron move from base to collector, and once they reach from base, they have to go to collector. So, choice A is suitable. You have to rule out whether other three are not okay. Electron move from base to collector. Collector collects those electrons. A is the choice. This is the transfer characteristics that they have shown in the next question. And for using transistor as a switch, they are asking which part of the characteristics we are going to use. Either you use 3 only, both regions 1 and 3, or region 2 and 3, or region 1 and 2. I have suggested that this mid region will almost have same slope. This is the active region, which is only for amplification. So, therefore, the choice should be this and this, not this. So, 1 and 3 are used for transistor to work as a switch, and that option is there in B, both in region 1 and 3. A transistor is operated in common emitter configuration at Vc equals 2 volt, such that a change in base current from 100 microampere to 200 microampere produces a change in the collector current from 5 milliampere to 10 milliampere they have given. It means that this is change in the base current. So, I can write it as delta IB, which is 200 minus 100 microampere, which amounts to 100 microampere, and change in collector current means delta IC, and that is 10 and 5 milliampere, that is 5 milliampere. Current gain means beta. Beta of the transistor is given by delta IC by delta IB, which amounts to 5 milli divided by 100 micro. Now, this is 5 into 10 raised to minus 3, and you can have 100 into 10 raised to minus 6 means 10 raised to minus 4. That minus 4 comes to the numerator, it becomes plus 4. So, this translates to 50. So, D is the choice. And the next question, for a transistor amplifier, the voltage gain is high at high and low frequencies and constant in the middle frequency range, is low at high and low frequencies and constant in the middle frequency range, remain constant for all frequencies, is high at high frequencies and low frequencies and middle frequency range. Basically, transistor amplifier, when you take CE mode, you will be getting this kind of a response for the frequency versus voltage gain. So, you can see in which choice you will have at low frequency and high frequency, low value is low at high and low frequencies and constant in the middle range. So, choice B is correct for this particular case. A common emitter amplifier has a voltage gain of 50. So, it is AV equals 50 they have given. An input impedance of 100 ohm and output impedance of 200 ohm. They want power gain. See, if you want power gain is given by voltage gain into current gain. So if you want to know that, so you go for AV equals, basically this can also be written beta. Beta is current gain. AV is beta into R naught by Ri. So this AV is 50. 50 equals beta into 200 by 100. This will cancel it twice. 2 beta equals 50. So beta equals 25. Now you go back and substitute. Power gain AP will be equal to AV is 50. That is what I have substituted here. And AI, that is beta, is 25. So 25 into 50 is 1250. The choice is C. In the following common emitter configuration, an NPN transistor with current gain beta equals 100 is used. The output voltage of the amplifier will be, basically if you want to know output voltage V0, it is AV into VI. So our job is to see, VI is given already, your job is to calculate what is AV. Now AV will be equal to, you will have beta into RL by Ri. Beta they have given 100 here, so 100 into RL is 10 kilo ohm, so 10K, and Ri is 1 kilo ohm. So this will go, this is 1000, which means 10 raised to 3. Now you substitute, V0 will be equal to, AV is 10 raised to 3, Vi is millivolt. 1 millivolt means 10 raised to minus 3. This will make it 1. So V0 is 1 volt. So C is the choice. The input signal given to a C amplifier having a voltage gain of 150 is given by Vi is equal to 2 cos 15t plus pi by 3. The corresponding output signal will be, the output signal V0 will be equal to AV into Vi. So AV they have given 150. So 150 magnitude wise into 2 you see. So 300 will come, and the rest will be what equation will be there. Remember, in C amplifier, if input is like this you take, output will be out of phase with respect to input by 180 degree, that is pi radian. So what you should do is, you have to go by what is the phase, 15t plus pi by 3 plus another additional pi will come. This will make it like 3 pi plus pi, 4 pi by 3. So along with 15t, where is that 4 pi by 3 you see, and this amounts to 300. So the answer is C, 300 cos 15t plus 4 pi by 3. In the circuit below, A and B represent two inputs and C represents the output. The circuit represents which of the following gates, like AND, NAND or NOR. Now these are basically two parallel lines. Now whenever you give inputs like 0, 1, etc., then both will either conduct or anyone can conduct. Since this is either this or this kind of line, you can assume that this will represent OR gate, because if you take that these are 0, 0, inputs are 0 and 0, there is no output, it will be 0. If you take 0 and 1, then second diode will conduct, again you will be realizing output, so it will be 1. If you take 1, 0, the first diode will conduct, again you will get output 1. If both are 1, then it will give 1 because both of them are conducting, and you will be realizing output from this point to this point. So this represents actually an OR gate. Identify the operation performed by the circuit given below. Now a shorted input NAND gate or a NOR gate. This is basically a NOR gate, shorted input. it will behave like a NOT gate. So the output of this will be A bar and the output of this will be B bar. You are giving it to basically another NOR gate. Imagine first without the bubble it will appear like a OR gate. So essentially what happens is you are having output A bar plus B bar, but then this bubble is there, you have to write one more bar, and there is this De Morgan's theorem which states that if you are having inputs like A plus B, if you take the entire bar, it will be written like A bar dot B bar, or if you are having this as the input, this can be written like this. You can remember De Morgan's theorems by stating that break the line, change the sign like. So you are having this line, you have broken it, you have changed the sign from plus to dot, dot to plus. If you go by that, this will be written like A bar bar, and this is dot, now change the sign, so B bar bar, it is AB. AB means it is ANDing, so this represents basically AND gate. So 3 NORs in this combination will produce an AND gate. To get an output 1 from the circuit shown in the figure, the inputs must be. Now look at this last gate. This last gate is essentially AND gate, and you require an output 1. That's what they say. If you want an output 1 from an AND gate, then both its inputs must be 1, and this invariably means C must be 1, and C is 1 in only one choice. So you need not look anywhere else. This will be the choice for you, because this being OR gate, even if any one of the input is high like 1, it will return with a 1. So answer is C. The following figure shows a logic gate circuit with 2 inputs A and B and the output Y. The voltage waveforms of A, B and the output Y are as given. This is a timing diagram. You have to see how exactly in every particular time interval the signals are taken. Now this is 1 high and high. For high and high you are getting nil, that is 0. So you can write it like 1 and 1, you are getting 0. And go to the next time interval, 0 and 0 you are getting 1. And next time interval, 0 and 1 but still 1. And the next one, 1 and 0 but still 1. Now this kind of gate will be a NAND gate. NAND gate will be exactly opposite to an AND gate. So in AND gate you will see that the first one should give you 1, but it is giving 0. 1 and 1 is 1, but inversion of that is 0. So this must be a NAND gate. The combination of NAND gates shown here are equivalent to. So you are having A, this becomes A bar, shorted input NAND will become a NOT gate. This also will be like B bar. A bar and B bar are fed to an AND gate. So it is like saying A bar dot B bar, and then you are taking the inversion with this bubble. Now this can be written like A bar bar plus B bar bar. This is A plus B. This represents OR gate. So this will be an OR gate, and this is an AND gate. NAND gate basically is giving AB bar, and a shorted input NAND gate acts like AND gate NOT gate. So it acts like a NOT gate. So if it is acting like a NOT gate, AB bar is already there. One more bar means this becomes AB. So essentially this is AND gate then. So this means OR gate is there and AND gate is there. You can go for A. Now coming to the next topic, communication. Few questions are here. The electromagnetic waves of frequency 2 megahertz to 30 megahertz are used. Now since this is More than 2 megahertz, it cannot be ground wave propagation, this is ruled out, and 2 to 30 megahertz will be used in skywave propagation, you can go for it. Microwave and satellite, they go for gigahertz range, much higher than that. Then a modem is what? It is a combination of both modulating and demodulating device. So in that name itself you can see modulate and demodulate part is there. So it is modulating and demodulating device. Then arrange the following communication frequency bands in the increasing order of frequencies. Now start from lowest frequency communication, you can go for this the first one, and so you can say 1, and immediately after that this is the second one. So second one is FM broadcast, that is 3. After 3 you go for television, this is 4, 1, 3, 4, and cellular will come 2, satellite highest frequency 5, 1, 3, 4, 2, 5, that happens to be A. 3 waves A, B and C of frequencies 1600 kilohertz, 5 megahertz and 60 megahertz respectively are to be transmitted from one place to another. Which of the following is the most appropriate mode of communication? Now you can see 1600 is A, that is low frequency, less than 2 megahertz that is. So naturally it must be via ground wave. So you can say 1000, so this is ground wave propagation A, and then second one is 5 megahertz. 5 megahertz cannot be ground wave, and it cannot be space wave because it is less than that, very small frequency compared to that. So it comes in the mid frequency range. This is via sky wave, because in sky wave propagation you have the ionospheric layer reflecting these kind of waves, this frequency range. And the last one is 60 megahertz, that cannot be sky wave because that will be penetrating that ionospheric region, and it can be only used for space wave propagation. So this will be space. So A is you can say ground wave, and that is given here. A is transmitted via ground wave, B via sky wave, C via space wave. So we can go for choice B. In satellite communication, the frequency used lies between 5 megahertz and 10 megahertz. The uplink and downlink frequencies are different. The orbit geostationary satellite lies in the equatorial plane at an inclination of 0 degree. They are asking which of these statements is true. Like, say the frequency used lies between 5 megahertz to 10 megahertz they have given. This generally will be for skywave propagation. For satellite it will be much higher. So naturally first one is not okay. Then second one, the uplink and downlink frequencies are different. Usually that is the norm. There will be different frequency ranges for those uplink and downlink. So second one is true. And the orbit of geostationary satellite lies in the equatorial plane with 0 inclination, 0 degree. That is also correct. So the right option will be 2 and 3 are correct. So A is the answer. The distance of coverage of a transmitting antenna is 12.8 kilometer. Then the height of the antenna is. So what you can do, you have this equation, D is equal to root of 2RH. You square it, D square is equal to 2RH, where R is radius of Earth. You want to know what is H. So D square by 2R you can do. D in this case is 12.8. Since it is squared, I will write it twice. And kilo is there, 10 raised to 3 and again 10 raised to 3. And now 2 into this 6400, I can write it like 6.4. Then 10 raised to 3 will come out of it. Again kilometer is there, one more 10 raised to 3. So these will get cancelled. And 6.4 into 2 is 12.8. Then that will get cancelled. You are left with 12.8 meter as the antenna height, which is choice B. A signal of 5 kilohertz frequency is amplitude modulated on a carrier wave of frequency 2 megahertz. The frequencies of the resultant signal is R. Now what happens, I told you, carrier frequency, if it is Fc, that will have sideband frequencies Fc plus F, the message signal frequency, Fc minus Fm. What you can do, this 2 megahertz, this is in kilohertz, so you can convert megahertz to kilohertz. This will be 2000 kilohertz, and this is Fm, modulating signal frequency. So you can add 2000 with 5 kilohertz, or you can subtract 5 kilohertz from 2000. So if you do subtraction, you will be getting 2000 minus 5. This addition will give you 2000 plus 5. So the answers will be 2000 should be there, and then 1995 and 2005, and that appears in C. A basic communication system consists of transmitter, information source, user of information, channel, receiver. Now this is a knowledge based question. You should go back to the basic block diagram that you have seen in textbook. You will find that answer is, first you should have information source, so B, then a transmitter should transmit that, so you will have A, and then via a medium it should transmit it, so channel is required, D, and next is there must be a receiver, E, and the receiver gives the information to user of information, this is C. So BADEC, and that is choice B. So I wish all the students all the very best for. I thank all the students for watching this video, and these educational videos which are organized by PU Education Department are available on the PU Education website, and you can go to the YouTube and you can watch these videos any number of times, anytime also. Make use of these videos, students. All the very best for your examinations. Any amount of preparation for any entrance examination will not be totally sort of complete. The more number of questions that you practice, numericals that you practice, the better it will be. All the very best. Thank you.